So this is the title of the lecture which I am giving now. This is 60 years of lasers and 120 years of photons. As I said, we had very many landmark years in the past couple of decades. In 2005, we had 100 years of photons. And I prepared a lecture at that time. Then the title of the lecture was Century of Photons. And after 5 years, in 2010, we had half century of lasers. So from that time onwards, I gave this lecture, Century of Photons and half century of lasers. Okay. And then in 2015, we had the International Year of Light. Now, this is very interesting period. I will explain that. It was inaugurated in Paris on 19th and 20th of January in 2015, and the International Year of Light coincided with the 1000 years of Ibn al-Haytham's book on optics, and the name of the book is Kitab al-Manasir, and the book is a kind of a collection of knowledge from all parts of civilized world at that time. Please remember, it is not a contribution by Haytham alone. He collected all the details that were available at that time from India, for example, and from Egypt and Mesopotamia, Syria, and so on. And then this book, Kitab al-Manasir, compiled all the knowledge on light at that time. It was sponsored by the International Year of Light 2015, was sponsored by UNESCO, and it is being celebrated. It was celebrated by scientific community all over the world. And then this is something on Al-Haytham, a picture of Haytham and some of the optical instruments that he devised at that time, like a pinhole camera and a magnifying glass and so on. Now, this is the first page of the book translated into, I think, into Latin also. Al-Haytham's book's first page. Now, then came in 2017, we had 100 years of stimulated emission. That is 100 years when Albert Einstein proposed the idea of stimulated emission of radiation. So we had another international year on stimulated emission at that time. And in 2020, which is the worst year in the history of humanity, as you know, in 2020, we have 120 years of photons and 60 years of lasers. So we are having the diamond jubilee of laser this year. But unfortunately, the department couldn't celebrate the silver jubilee in a grand way because of corona problem. Same is true about the International School of Photonics at CUSAT. So is also celebrating its 25th year in an online manner, online mode. So let's talk about something more on light. As you know, it's the most astonishing of natural phenomena. And I'll give you some early ideas on light. These are all well known to you. As I said, it's a popular lecture, not a research material. And then I will just mention some of the Indian contributions from Vedic period and later on. And then we come to the modern period, when Newton and others started to talk about the details of light, nature and properties of light. Then we have to mention, of course, Maxwell's grand synthesis through the so-called electromagnetic theory. And then come Planck, Einstein, and the century of photons. And then we will discuss the era of lasers and photonics and optoelectronics. So that's the general plan I was thinking about. Now, as I said, all the knowledge on light was not by other people, Europeans or Egyptians or Arabs. In India, we had considerable knowledge on the nature of light in early period. An example is given here. This is a sloga by a sage Vadeshwar. It's a hymn to the sun god. Sun, as you know, is the greatest source of light that we can see from here on earth. Now, it says that it's a stanza from the hymn. And this stanza says, Yojana sahasre dve shate dvecha yojane ekena nimisharthena ramanu namastu. The meaning is, hey sun god, you continue to send light to us at the speed of 2202. Dve sahasre 2000, Dveshade 200, and Dve 2. So light at the speed of 2202 yojanas in 1.5 nimisha, ekena nimisharthena, in 1.5 nimisha. 1 nimisha is the blink of the eye, which is roughly the persistence period of the eye, which is 1/18th of a second. So if you calculate this, 1 yojana is about 11 kilometers. So 2202 into 11 divided by 1.5 divided by 80. It works out to be 290,664. Just see how close it is to the modern value of speed of light. So the people in those days had possibly clear idea about the speed of light and other properties of light. There is a chapter in what is called Bharadwaj Yantra Samhita, and this chapter is on Prakasha Samhita. And in that, various optical instruments are described, and a lot of properties of visible light described in that. So remember, the speed of light is calculated in 8th century. How many centuries before Michelson and Morley and others? Well, what are the light sources we have? No doubt, the sun is the greatest of the sources. Only thing is that it is 150 million kilometers away, and it sends everything to Earth: light, heat, energy, everything. So we live on this planet just because of this huge source of light. And then we have artificial lights, and the evolution of light is very interesting. In an early period, human beings had light from lamps, and these lamps were lit with the fat from animal fat, and then we have the oil lamp and candle light, and then this is the hurricane lamp. The present generation, I don't know whether the present generation of students and research scholars have seen what we call a hurricane lamp. It's actually a hurricane lamp. In our younger days, we used to carry this, and this is the electric light. And that, of course, appeared at the end of 19th century. And if you ask me what is the greatest invention by a scientist in 19th century, without any doubt, I can say that it is the invention of electric bulb by Thomas Alva Edison. Edison changed the history of humanity. He gave us 24 hours in a day. Before the electric light came into existence, humankind did not possess 24 hours in a day. When night falls, everything is in dark, and there was no social life with that kind of ambience. So the electric light changed everything, and in fact, we should say that the modern civilization starts from that period. Then the electric light itself underwent several changes. We had the fluorescent lamp, compact fluorescent lamp, LEDs, and so on. So the lighting technology progresses at a prodigious speed. Well, that itself is another topic for discussion at length, but I am leaving it at that. Now comes the question, what is the nature of the light? And in this case, of course, everybody knows that light is a form of energy. But what it exactly is something which has been discussed by very many scientists. And when we come to Newton, we find that 300 years ago, Newton proposed that Newton proposed the particle theory of light, or he proposed the corpuscular theory of light to explain the various characteristics. His quotation is, "I think light is a stream of tiny particles called corpuscles." So this he describes in his book Optics, a treatise on light. Now Newton thought that a source of light should be emitting particles, because if you put a barrier through which light does not pass, then you get a shadow. Obviously, this is due to the fact that the barrier obstructs the passage of these particles, and that's why we get a shadow. But if you assume that light is a kind of a wave, then when you place a barrier, then these waves should bend around the corner of the barriers. That was not seen very clearly at that time, but later people found it out, as we see later. And at the same time, some people said that light is not particle. Light consists of waves. And the first, there were many, of course, starting with Thomas Young and Huygens and Fresnel and Hooke and so on. So the experiment by Young is very famous. It is called Young's double slit experiment. That's a fact which demonstrates the interference phenomenon of light. If light is a wave, then waves should interfere. And in this double slit experiment, the wavefront from both these slits should interfere, and it should give you regions of darkness and regions of brightness. So you get interference fringes. And Thomas Young demonstrated the existence of interference fringes. And he was convinced that light consists of waves in some medium. And as I said, as I showed earlier, if light is a wave, then it should bend around the coordinates. So that was demonstrated by Augustine Jean Fresnel, and he showed that if you put a single slit, then on either side of the image of the slit on a screen, you get dark and bright fringes, which is what you expect if light consists of waves. So by the middle of 19th century, many people thought that light is a wave, and Newton's corpuscular theory of light went into shadows for some time. Wave theory gained strength because of all these experiments on interference and diffraction, and then polarization and so on. Well, the real breakthrough comes. If light is a wave, then what kind of wave it is a question. People measured the velocity of light, and it turned out to be very large, 300,000 kilometers per second. And if it is a wave, then the medium which carries these waves must be having what you call enormous values for its elastic constants. Then only such rapid vibrations are possible. And that medium was supposedly called ether medium, and the vibrations in the ether medium is the phenomenon of light, was the idea at the middle of 19th century. In 1864, James Clerk Maxwell came out with the exciting idea that light, of course, is a wave, but the nature of the wave is not mechanical. The nature of the wave is electrical and magnetic. And that's the electromagnetic theory of light. And as you know, the electric field fluctuations will give rise to magnetic field fluctuations, and magnetic field fluctuations should give rise to electric field fluctuation in vacuum also. One of the most important contribution of, actually it's only Faraday's laws rewritten by James Clerk Maxwell. Faraday said that if there is fluctuation in magnetic field, it should produce an electric field. Maxwell said the opposite is also true. If there is a fluctuation in electric field, it should produce a magnetic field. But if there is a fluctuation in electric field, why should it produce a current in a vacuum? And that's where the idea of displacement current comes in. Even in vacuum, a fluctuating electric field can produce a current, and this current is a displacement current, and the result of the displacement current is the creation of a magnetic field. So a fluctuating electric field will give rise to a fluctuating magnetic field, which in turn will give rise to fluctuating electric field, and both will aid each other and propagate in the forward direction. And from the set of equations which he wrote, Maxwell could easily work out the velocity of light. It's closely related to the empty space. The electric and magnetic susceptibilities of the empty space will determine the velocity of light, which turned out to be exactly what was measured by experiment. So electromagnetic theory is quite a success. And apart from the fact that it's a success, Maxwell achieved a kind of synthesis which is unique in the history of physics. The synthesis is achieved is fantastic. All kinds of radiating energy, starting from starting from invisible electromagnetic waves to visible electromagnetic waves, again long wavelength electromagnetic waves, heat waves, light waves, sound waves, ultraviolet, not sound, heat waves, violet light, ultraviolet light, infrared light, X-ray, everything could come under one umbrella, namely electromagnetic phenomena. So that is a great synthesis which was achieved by James Clerk Maxwell, and you wouldn't see such a grand unification in the history of physics, except possibly on this unification of fields later on. Well, here is something which is useful or worthwhile considering. Now, if one asks the question, what do you really see in this world? If you take the whole electromagnetic spectrum, you will find that it consists of extremely short wavelengths, from gamma rays, which have wavelengths of the order of 10 raised to minus 12 of a centimeter, and high energy cosmic rays, which may even have wavelengths of 10 raised to minus 15 centimeters, and so on. Several orders of magnitudes of wavelength changes are there, and then we come to a small medium, 8 micrometer to 0.4 micrometer. That's what we see of this huge gamut of wavelengths. We are able to see from 0.8 micrometer to 0.4 micrometer. And everything outside of that is not visible to us, And then on the longer wavelength sides, we have infrared, microwaves, radio waves, and long radio waves, and so on. So it is through this narrow slit that we observe the universe without aids. Our eyes are sensitive only to this region, and this means that we hardly see anything in this universe. And whatever we see through this narrow slit of electromagnetic spectrum need not be the reality. There may be shadows of reality. That's what William Röntgen and others said. So this may be, it was Bragg who really said, we don't see reality. William Bragg said, we don't see reality, but we see shadows of reality. So only through this narrow window we can see the shadows of reality. Of course, there is a lot of philosophy coming at this point. I will just talk about, in fact, I'm writing an article on that. It's about a professor, Ronald Hoffman of University of California, who just published a book about what do we perceive in this universe. And Ronald Hoffman has shown that we don't perceive reality. We are never designed to perceive reality in this world. What we perceive are only things which are absolutely essential for our survival. All other things are only shadows of reality. All our things are distorted realities. And Donald Hoffman's book has become very famous now, and based on that, I'm just writing a small article, which will be published sometime later. So here is a little bit of philosophy. Possibly it is the optoelectronics people or the photonics people who know that the world is a Maya. World is not reality, but it is a Maya. For example, if you take Aishwarya Rai and put her in ultraviolet light, you will see her as a ghost. Not joking, because she will be giving all kinds of luminescence and unwanted places, and she will look like a ghost. So beauty is not only skin deep, beauty is also wavelength deep. Okay. So, and then came another shattering piece of phenomenon, shattering piece of experiment. And at the beginning of 20th century, people, just before that, a few years before that, people noticed that if you illuminate a metal surface with light in vacuum, then electrons are ejected from the surface. Now, this phenomenon is called the photoelectric effect. And as you know, you have studied this in elementary class. Most have noticed this in elementary classes. How come electromagnetic waves knock out electrons from metal surfaces? If you make a classical calculation, there is no chance that electrons are ejected. And it is at this point that Albert Einstein in 1905 came up and said, look, we should consider not only the wave aspect of light, light also has a particle aspect, just as enunciated by Max Planck in the year 1900. He told that radiation consists of packets of energy, and it's not just a wave, and all these packets, he didn't say that the packets are being propagated as packets. It was Albert Einstein who confirmed that the packets of energy are being propagated through space as packets itself. So in that case, light should also behave as a corpuscle, and that's exactly what one has in the case of photoelectric effect. The particle of light hits an electron and knocks it out. It's a collision between an electron and the light particle. The name photon was not there. The name photon came much later. It's only in 1924 the particle of light as photon. So from that day onwards, we call the particle of light as the photons. So the light particles come and hit the metal surface and knock the electrons from the metal surface. The electrons are held with certain minimum energy in the metal surface. If W is that energy, the incident photon energy must at least be equal to the binding energy of the electron, which is called the work function, and there is a frequency minimum for photoelectric effect, which was all experimentally verified. And it doesn't matter whether Einstein drinks the coffee or monkey drinks the coffee, whatever is not there must go to their stomach. Okay, that's the idea. So if the frequency is greater than the minimum, then the outcoming electron will have certain kinetic energy, which is the total energy minus the work function. Okay. Now at this point, Arthur Holly-Compton tried to prove that light is really a particle, and it can collide with electrons and it obeys the laws of collision. Now, he didn't choose visible light for his demonstration. He chose X-ray photons. The particles of X-rays were chosen for this, and Compton did the experiment, and the experiment was scattering of X-rays by electrons. So he had a target full of electrons, actually carbon atoms, and he directed his X-ray beam to that, and the incoming light particles collided with the electron, and it is a kind of a elastic collision, and in the elastic collision, using classical mechanics, we can show that the scattered particle would have lost some energy. The loss of energy during collision is, I think it's a elementary calculation in classical mechanics. So if the electron lose its energy, sorry, if the light particle loses its energy, then naturally its frequency will reduce and its wavelength will increase. So Arthur Holly Compton looked for, is there any change in wavelength for the scattered X-rays? And lo and behold, he found that there is a change in wavelength for scattered electrons. So it is angle dependent. So when the angle changes, there is a maximum value for scattered X-ray wavelength change, and it's given by this formula. It's about 0.048 angstrom unit. Remember, the copper K alpha X-ray lines which he used had only 8 angstrom wavelength, and measuring a wavelength change of 0.048 angstrom in 8 angstrom unit is a very tough job, but Compton did it very nicely, and he showed that scattered X-ray beams suffers a loss of energy and there's a change in wavelength, and Compton gets the Nobel Prize for showing that the X-ray photons, that it is almost at that time the name photon was proposed by G.N. Lewis for the X-ray quantum. So the collision of X-ray photon and the electron is elastic, and there is change in wavelength. As soon as Sir C.V. Raman heard about the Compton effect, he was sure that if this is happening in X-ray region, it must be happening in visible light region also. So he did a series of experiments to see that if there is any change in wavelength for scattered beam. And as you know, the history tells you that in 1928, he succeeded in demonstrating that there is a change in wavelength during scattering process of light from molecules. But this process is not akin to X-ray scattering. The process is entirely different. This is not an elastic scattering at all. It is an inelastic scattering. And that's what happens in Raman. Of course, there is a component which is elastically scattered, and that elastically scattered photon will give rise to the so-called Rayleigh line. The light photon, the photon hitting the molecule, if it is scattered elastically, there is not much change in wavelength, because you know the change in wavelength is extremely small. So the Rayleigh line is almost at the same frequency as the incident photon, and if the incident photon excites the molecule, the incident photon will lose energy, and it will get scattered with a longer wavelength, and that's called the Stokes-Raman radiation. And if the incident photon gains some energy from the molecules, then its frequency will be increased and the wavelength will be shifted to blue, and the scattered photons will appear on the blue side of the Rayleigh line, and they are called the anti-Stokes line. I don't have to explain this to a department which is doing tremendous amount of work in laser Raman scattering, but you can look at the phenomenon and compare it with the Compton effect, where it was an elastic scattering, and in the case of Raman effect, it is an inelastic scattering, where the photon exchanges energy with the internal energy of the molecule. It could be the rotational energy or vibrational energy or even electronic energy of the molecule. So that is Raman effect in sum and substance. This is one of the brightest and most important contribution in the field of light by an Indian scientist. Possibly after Vadeshwar, we should recall Raman in modern times for finding the great phenomenon of Raman effect. Now comes another very interesting phenomenon, air production. If you have very high energy photons like gamma ray photons with energy just over 1 million electron volt, and if it gets scattered by a heavy nucleus like lead nucleus, then what happens is that the gamma ray disappears and an electron-positron pair appears in its place. So this is a case where energy disappears and matter appears. So one of the best demonstration of materialization of energy happens in this case. Gamma ray gets scattered and the gamma ray disappears, and instead you get an electron-positron pair. And that happens provided the incident gamma ray has a minimum energy of 1.01 million electron volt or so. So it's a very spectacular phenomenon. This was discovered in cosmic rays by Anderson and others. They all get Nobel Prize for that. Another very important and practically useful phenomenon is the so-called positron annihilation. Now, if an electron meets a positive electron, which is positron, then what happens is that both electron and positron disappears. Instead, you get a pair of gamma rays which fly off in the opposite directions. So, if you have electron-positron pair meeting each other, then a pair of gamma rays flying in opposite direction should appear. Okay? And this is called, the process is called the positron annihilation. The gamma rays will have energy of the order of 0.505 million electron. So it's very easy to find out a gamma ray which has been produced from positron annihilation. The energy is almost exact, and it should be accompanied by an exactly similar gamma ray. Now these gamma rays will have energy 0.505 million electron volts, and they should be flying off exactly in the opposite direction. So what I was telling was, it's easy to identify gamma rays produced in a process called electron-positron annihilation. This is extremely useful. This is the phenomenon which is being used in what is called PET scanners. The PET scanners are or positron emission tomography process. They make use of the phenomenon of positron electron annihilation. If a patient has cancerous region, they inject, the doctors inject a compound which emits, radioactive compound which emits positrons. Now, because of the high metabolism of, rapid metabolism of the cancerous region, they preferentially accumulate in the cancerous region. And when in that region, the emitted positron immediately comes across an electron outside, and they get annihilated, and then you have two gamma rays going in opposite direction. So it is easy to detect these two gamma rays flying in opposite direction, because all that you have to do is to put two gamma ray detectors exactly 180 degree apart, and then rotate the whole thing along the whole body scan, and then you can pinpoint the position from where these radiations are coming. So you can really locate malignant regions using positron emission tomography. And the principle behind it is positron annihilation process. So one of the most useful phenomenon where light is really made use of in cancer detection. Well, and then this is a big question. This is something which students always ask you. How does an electron know that there is another electron in the vicinity for them to repel? Only if I know that there is an electron in the near vicinity, and then I can, the first electron can repel the other electron. How is it? It's knowing that there is another electron. Our standard answer in the classrooms are that an electron produces an electric field, and the second electron is in the electric field, and then it experiences a force. Well, that's not an honest answer. It's a roundabout answer. It was Richard Feynman who gave the right answer. He said that the electron can always emit a virtual photon, and these virtual photons can be taken back before they are discovered. because the virtual photon emitted can exist for a short time duration delta t, such that the product of the energy of the emitted photon and delta t should be of the order of h. If delta E is the energy of the emitted photon and delta t is the duration through which it goes out and comes back, then delta E, delta t should be of the order of h, Planck's constant. So every particle like electron is a source of virtual photon, and they continue to emit virtual photon and take them back. In other words, it's, and then it comes in contact with the second electron, and the second electron immediately gives back an electron to the first. So when the first electron emits a photon has a momentum h nu by c. So it's giving a momentum to the second electron, and when the second electron is throwing it back to the first, it's throwing back the momentum. So a momentum exchange is actually equal to the force. I used to tell a small analogy to the students. It is just like if you have two persons standing on an ice skating board with skating shoes, and if the first person has a volleyball with him, and if he throws the volleyball to the second person, the first person, when he throws the volleyball, he moves back because there is a recoil. And when the second person holds the volleyball, he also moves back because there is a momentum which he receives. If the second person throws it back, again he moves back, and the first person who receives it will again move back. So by throwing the volleyball back and forth, the two persons will move apart. It is as if a force is acting between them. Exactly the same process is happening between the two electrons. They are throwing back and forth the photons, and this way they exchange momentum and they experience a force. Now, then comes the most important thing. The photon is a force mediating particle. Photon is a boson, and it is the particle which mediates the electromagnetic force. So that's the great place we give to the photon. Photon is no ordinary particle. It's a force mediating particle, and it is a boson. Of course, I didn't discuss the contribution by S.N. Bose. So that will take us from the main theme. So Bose was the first one who proposed that the photons are like molecules of a gas, and then you can apply statistical laws to that. And that resulted in Bose-Einstein statistics and so on. I don't want to go into that aspect of photon. But here you see that photon is a force mediating boson. That's a unique position for photon. And that's what we call this explanation, which is what is called quantum electrodynamics. Now, I will give you a simplified version of quantum electrodynamics. In fact, I have done this long ago, and I think I have printed this in Bulletin of Indian Association of Physics Teachers, somewhere like that. Now, delta E is the energy of the photon, which is temporarily loaned, and delta E is the time, then it should be of the order of h nu. This delta E is h nu, and delta t is the distance between the electron divided by velocity of light, r by c. Then if you do a little bit of algebra, then you finally show that the force is inversely proportional to the distance. So the Coulomb force can be inversely proportional to the distance. This is a heuristic derivation. Don't think that this is exact. This is a heuristic derivation. Exact derivation, of course, is given by Richard Feynman, for which he gets Nobel Prize. Well, those are the things until the middle of 20th century. No, of course, Feynman's theory comes much later. Now here we had 50th anniversary celebration of Ted Mayman's laser 10 years back. And that's another path-breaking landmark in the history of physics. It's a watershed in the history of physics and in the history of technology and in the history of optoelectronics and photonics. It's the beginning of photonics and optoelectronics. And that happened almost in 1960. In fact, towards the closing years of 1959. The history is very long. Of course, people like Professor Gattak are here, who are very well versed and conversant with the history of lasers. So I don't want to go deeper into those aspects. The only thing I will say that poor Theodore Mayman didn't get a Nobel Prize because the paper which he sent to Physical Review Letter was reviewed by Arthur Shallow, who himself was trying to discover laser. So his paper was rejected and he didn't get the Nobel Prize. Poor fellow. Mayman's Ruby laser, we all teach this and we learn this, and Ruby, as you know, is when you study optoelectronics, the students, when you study, you know that Ruby is one of the worst thing, and possibly Mayman was very, very lucky to get lasing out of this Ruby. It's a 3-level system, most inefficient, and the pumping process also is not very efficient. It gives you output at the 694.3 nanometer deep red radiation. So I don't want to describe this except to show that in 2010 we had the half century of photonics or photons of lasers. Now the properties of laser beam. I need not carry code to the Newcastle. Every optoelectronics student here and experts know the properties, but just for the sake of completeness, let me go through this. They are highly coherent and extremely directional. It has very high power densities. This is a calculation which students can try to do. You take a say 1 milliwatt helium neon laser and try to focus it to a point which the limit is lambda by 4, and just find out what is the power density at the focal point. The 1 milliwatt helium neon laser will give you a power density of 40,000 watts per square centimeter at the focal point when it is finely focused. Only a coherent beam can be focused to that limit. Incoherent beams cannot be focused to that limit. So you can get extremely high power densities with laser beam because they are coherent, and they can have very high peak power when they are pulsed. You can pulse them at milliseconds and microseconds and nanoseconds and femtoseconds and so on. And as you go on compressing the pulse shorter and shorter duration, the peak power goes up. Simple calculations will show you. Now they are capable of producing many non-linear effects. Well, that's also another interesting aspect regarding the history. In electronics, I can have a frequency f, and then I get its second harmonic, 2f, get it third harmonic, 3f, and so on. So you can double the frequency. If I have two frequencies, f1 and f2, I can add them together and get f1 plus f2 in electronics. And that's what we do in heterodynamics. We have frequency f1, the local oscillator f2, then f1 minus f2 will give you the intermediate frequency if, which we amplified at a fixed frequency. So these are all parts of the standard electronics. And when we come to nonlinear effects of laser beams, we see that we can do all these things like getting second harmonic, adding two frequencies, subtracting two frequencies, up converting frequency, down converting frequency. All these we can do with laser beams as well. So we started calling this field in those days, in the 70s and 80s, we started calling this field as quantum electronics. Somehow I find that after so many years, the name quantum electronics did not get stuck. Possibly the two names which got stuck with this field is, one is photonics, of course. It is now called photonics and optics. Of course, the name optoelectronics was strong once upon a time, but now people do not want to call it optoelectronics. Photonics has better weightage when it comes to the topic as a whole. Well, anyway, these nonlinear effects made it possible to do things which are possible with the simple frequencies in RF field. So quantum electronics was the area in which these nonlinear effects were performed. Of course, now I don't know. There are books on quantum electronics. Nobody calls them quantum electronics anymore. And some lasers can be tuned, so you can change the frequency. Well, this is it's an area which takes a longer time, and each one of them is a topic for at least 1 hour discussion. But due to lack of time, let me go through them in a cursory manner. As I said, in 1917, Albert Einstein proposed the idea of stimulated emission. The idea lay dormant for a very long time, and people tried to do stimulated emission experimentally, but didn't succeed until possibly in 1954, when Townes, Gordon, and Sager produced the first microwave amplification by stimulated emission of radiation. The process of stimulated emission was demonstrated in the Maser equipment made by these people. And then why this is not possible at optical frequencies? It's a very valid question. You know, in microwave frequencies, you can produce a cavity. You can have a practical cavity which contain a number of modes. The microwave frequencies are of the order of centimeters and so on. So if you take a cavity which is few centimeters in diameter, the number of modes of electromagnetic waves is very definite, very finite. But light waves have wavelength of the order of fraction of a micrometer. So if you take any sizable cavity, there will be millions and billions of modes. Now, if you want to amplify a particular mode, it is absolutely essential to select that. Out of billions of modes, how to select a particular mode is a tough question. And the partial solution was provided by Townes, Shallow in America, and Nikolai Basov and Prokhorov, Alexander Prokhorov in Russia. They said, let's do it this way. Let's take a Fabry-Pro interferometer and move the mirrors to a fairly large distance. You know, as normal Fabry-Pro has a mirror which is separated by a fraction of a millimeter. So, but if you move these two Fabry-Pro mirrors M1 and M2 to a greater distance, still it is a Fabry-Pro. But then this Fabry-Pro can contain a large number of modes which are traveling along the axis of the Fabry-Pro. If any off-axis mode is there, it gets out of the cavity. This is a cavity now. The open resonator is a cavity now, and any off-axis mode just gets out, and the number of modes which are contained by the parallel mirrors will be finite. And that's a very clever idea. Of course, there are stories how Shallow happened to hit upon this idea and so on. So they propose an open resonator which will provide as the cavity for optical masers. And it was Theodore Maiman who succeeded first, because he took a cigar-shaped ruby and polished it at two ends, and then that provided the optical resonator. And Maiman's laser gave out first burst of coherent light. Now, if you look at the history, it is more than light which bolted out of Maiman's laser. It was a revolution which came out of Maiman's laser. And that started the laser revolution. A whole revolution was shot out from the first laser made by Theodore Maiman. 2 weeks later, actually, Bennett, Javan, and Harriet in uh, Bell Laboratories made the first gas discharge laser, which was a helium neon gas laser, which gives, as you know, it is a standard laboratory tool now. It gives you 632.8 nanometer red radiation, and it has excellent coherence length and coherence time, and very good for doing many experiments. And then came the neodymium glass laser, or neodymium YAG laser, yttrium aluminum garnet doped with the neodymium 3D plus, neodymium 3 plus. So the neodymium laser also is the beginning of another revolution, because unlike ruby laser, the neodymium YAG laser is a 4-level system, and it can be the laser is far more efficient, because you learn in students will learn it in textbooks that 4-level systems are far more efficient than 3-level systems, and pumping also is more efficient in the YAG laser, and the output energy also is very high. In fact, if Theodore Maiman had used ND-YAG in here, it would have laced easily without any very hard pumping. But the problem is the output is not in the visible region. 1064 nanometer or 1.064 micrometer is the output wavelength for ND-YAG laser. It's not visible wavelength, whereas ruby gives you deep red light. But ND laser is one of the neodymium YAG or glass laser is one of the most important lasers. It's the workhorse for many laboratories. Another landmark is the discovery of long life semiconductor diode laser. And several people are there. Paul Suimatsu, the Russian scientists, they are all involved in this. And the initial semiconductor lasers had a short life, and the lasers with were produced by these people, and they had longer life, and that started the whole of communication revolution, the long-lived semiconductor diode laser. Okay, so communication revolution starts with this. Gallium arsenide was the first material which is used in fabricating the semiconductor diode laser, and with that came the entire band gap engineering and so on. We can have any wavelength from solid state semiconductor lasers now using band gap engineering. No time to go through the details. Carbon dioxide laser, C.K. and Patel, the Indian contribution in America. Patel became the director of Bell Labs. And he also became the scientific advisor to the President of the United States. CO2 laser, the first industrial laser, was the carbon dioxide laser, gives you two long wavelength infrared outputs, 10.6 micron and 9.4 micrometer long wavelength infrared, and this it has very high efficiency. At that time, this was the highest efficiency laser with great wall plug efficiency of as much as 30-40% wall plug efficiency for carbon dioxide laser. It is an industrial laser. You can do cutting, welding, and drilling, everything with CO2 lasers, and it is used in industry. For example, in marble cutting, in cutting Italian marbles, you can use a CO2 laser. So another big, powerful laser by an Indian scientist, C.K. and Patel. And argon ion laser. This is the laser which is used in all Raman and related studies. Of course, you can do Raman effect with helium neon laser, but argon is the best laser for doing Raman effect. It's a discharge laser and it can give you much more power than a helium neon laser. 12 watt. CUSAT had a 12 watt argon ion laser which was water cooled and so on. The total Wallplug efficiency is not good. We were putting in 48 kilowatts into it to get 12 watts of laser power. Okay. It gives you very strong 514.5 green line, which is excellent for Raman spectroscopy. I think Kerala University has Raman micrometer, which maybe make use of one of the argon laser. It also has blue 488, which is also very strong. It also gives you 456 and other lines, but these two are very important lines with sufficient power. You can do a lot of research with that, and you can also do laser shows with argon laser. So another important laser. Helium cadmium laser. I mean, just in the preview, I saw a helium cadmium laser in the department in Trivandrum. And the advantage with helium cadmium is that it gives you deep blue and ultraviolet. It gives you a 442 nanometer blue line, or rather violet line, and 325 ultraviolet line. So many of the photoluminescence experiments and fluorescence experiments, helium cadmium laser is good. But now this is being overtaken by semiconductor lasers. Tunable lasers, for example, you can use rhodamin dyes and excite them with other lasers and make them tunable. Dyes will fluoresce over a wide range of wavelengths, and then you can select a particular wavelength region. Wavelength selective element can be put in the laser cavity, and then you can tune the laser output using tunable lasers. So that was done by Sorokin and Lengard using rhodamin dyes. Excimer lasers are very useful for ophthalmic surgery. Xenon fluoride laser at 193 nanometer ultraviolet. It's excellent for laser ablation of human cornea and so on. So it's also used for laser deposition purposes, for making thin films. Free electron laser. I'm not much fond of this because one of my students worked on free electron laser for very many years to find out that it's not such an exciting laser. So I don't know whether there is any commercial free electron laser in the market, but they have its use, but it's not very popular laser. Alexandrite, it's another solid state laser, but more than Alexandrite, it is titanium, similar one, but it is titanium sapphire which is more popular. Titanium sapphire laser is a solid state laser, but it can laze in a wide wavelength region, starting with 665 nanometer to 1100 nanometer, and that gives you a broadband emission. And one of the advantages is that from that broadband emission you can do a process called quantum mode locking. So you do a mode locking and get a huge power output from titanium sapphire laser in a single pulse. So mode locking is easily possible with Ti sapphire, and all the ultra fast lasers like femtosecond lasers and picosecond lasers are made by mode locking the output of titanium sapphire laser. And then that's next, femtosecond. You do a mode locking of Ti sapphire. Michael Perry and others created femtosecond laser. I don't want to go into the details of that. CUSAT has a femtosecond laser which gives you 60 femtosecond output. And once you compress this into femtosecond, you get terawatt output. So you get tabletop terawatt output from femtosecond laser. I noticed Riju Isaac sitting in the audience, and he has been working with femtosecond laser to produce X-rays, because if you radiate any material with femtosecond laser, all the outer electrons of the atoms will be thrown up. The atom will be destroyed, and you start to get X-ray emission, and you can do even particle acceleration using femtosecond laser. This is very, very interesting. Gallium nitride violet laser, deep blue laser. This was discovered by the Japanese Suji Nagamura, and that itself is an exciting story. How Nagamura happened to make gallium nitride violet laser. People had thrown out gallium nitride as a no good material because it has lots of, when you make a crystal of gallium nitride, it has tremendous amount of defects and it will never lace. And Suji Nagamura made a very clever technique of making defect-free gallium nitride, and the first violet laser came out of it. Well, I had the opportunity to meet Nagamura in one of the international conferences where most people were giving lectures with red lasers, and Nagamura came onto the scene and he started to use his laser, which was blue, and we were all wonderstruck because the first time blue laser, of course, in the 90s, towards the end of 90s. Well, these are only a list of laser, but I will, the one laser which I have not shown here is the most important. So that's why I kept it to the last. That is a diode pumped solid state laser. The most efficient and most useful and most wonderful lasers are diode pumped solid state laser. Initially, we had used all these flash lamps and discharge systems for pumping a laser, but now you can have diodes with precise wavelengths, which will aim at the excitation levels, and then almost 100% of the pumping energy can be transferred to the laser system by this method. Now, discussion of DPSS, or diode pumped solid state laser, itself is a topic for elaborate discussion at great length. So I kept it for last to mention that this is a laser which needs a thorough understanding and a thorough study, and this is going to be the laser systems of the future. They are compact, they are highly power efficient, and you get a lot of output. I have a 532 nanometer laser pointer, which is a solid state diode pumped solid state laser. It's pumped with a diode. The diode produces output from an ND-YAG laser at 1.06. It is frequency doubled using potassium dihydrogen phosphate or something like that. And then you get 532 nanometer. Everything is the whole size of the laser pointer is just that of a pen, and all that you put in as energy source is two AAA batteries. From 3 volts, using AAA batteries, you get as much as 5 milliwatt, 532 nanometer green radiant. It is just something short of a wonder. So that's the laser that we should all love, the diode pumped solid state laser. Well, lasers have an umpteen number of uses. I cannot go into those kinds of things right now because I'm telling you the history of science, but history of light. But let me just show you one kind of measurement that you can do with a precision laser. This is a kind of measurement that is unprecedented in terms of accuracy and precision. Now, assume that you have a liquid droplet, a spherical liquid droplet, and then, of course, this is in, arrow is downwards. And then you put a laser beam into this liquid droplet, a spherical drop. This will undergo a number of multiple reflection inside, and that's called whispering gallery mode. This can now act as a sensor. This whispering gallery mode laser system can act as a sensor because you put in, sorry for this arrow, this down, you put in the laser beam and then it comes out at some point, and you watch the properties of the outcoming laser beam. if so much as the temperature outside changes by a nanokelvin, then it will be reflected in the properties of the outcoming laser. Say a few nanometer temperature variations can be measured using such whispering gallery mode sensors. This kind of sensitivity is unimaginable for any kind of conventional measuring systems. Okay, unprecedented and unimaginable. Now, similarly, if the gas composition outside changes little bit, then the outcoming laser beam will immediately reflect this aspect also. So you can sense the environment, you can sense the temperature, you can sense the pressure. Various things can be sensed with great precision using such sensors, which here it is one which uses the whispering gallery mode using it can be a diode laser. The whole thing can be very compact and so on. Well, here is just a demonstration of how you can use laser in biotechnology. See, here is a recombinant DNA, which is recombinant DNA, and this has been put into a living system, and then that fluoresces and shows its presence there in the fluorescence. And a purple laser has been developed in St. Andrews for this purpose. And when the organism multiplies, then you can trace that this particular gene goes into all that, using that. So you can do a lot of biotechnology using laser technology, especially laser fluorescence and laser phosphorescence. How much time do I have? No?
Yes, sir.
How much time do I have?
10 more minutes.
Okay, thank you. So we all saw the Young's double slit experiment, where the slits were mechanical slits, and the light was passing through the material and giving you the interference fringes. Now suppose instead of mechanical slits, I have two light beams, two ultra-fast light beams, and then I shoot a laser beam. These are laser beam, two pulses, successive pulses, and this, in synchronism with that, you shoot an electron beam. And then what happens? The electron get diffracted. So the light behaves exactly as their particles. Light behaves exactly as their mechanical slits. So in the encounter with the light pulses, the electrons behave exactly as light behaves with the encounter with material particle. So whether light is matter or not is debatable question. You get electron diffraction in this experiment. Well, this is another big area. I'm not going into it. I just show a little bit. Now, if you have an array of optical materials like this, these are microspheres of silicon or glass. Am I still audible because light? Is it okay? Can you hear me? Hello?
Yes, sir. Yes, sir.
Okay. So if you have an array of microspheres, then light of certain frequencies cannot propagate through that. It's just like electrons of certain energies cannot travel through a crystal because the electrons are waves and they get Bragg reflected from the layers. So just like that, the photons get reflected back and they cannot propagate. Such materials are called photonic band gap material. Just like you have electronic band gap material in solids for electronic propagations, we have the photonic band gap materials which can be created by stacking matchstick like silicon or putting glass spheres, like microspheres like this. And then you can make all kinds of cavity with that. Cavities can be constructed with the photonic band gap material. So light will be trapped here. So, well, I don't want to go into that. Yeah, you make a waveguide using this such the light passing through that using the photonic band gap material. So, see here, you have a path for light to travel. And these are all photonic band gap materials. So the light will not go into it. if you try to bend light like this in an ordinary material, then light will undergo total internal reflection, will not go this way. It will go this way only if it comes from the bottom. So using photonic bandgap material, you can take light to any point you want. Okay. So this here is an example. You send a laser beam, split it into two opposite directions, 90-degree turn for light. You cannot do that. You can do that with a mirror, of course, but you cannot do that with a surface which undergoes with total internal reflection. So, in fact, single atom laser, etc., can be made with that. Of course, I'll come to the last. Now, we have been talking about light and its speed is invariant 300,000 kilometers per second. But here is a wonderful experiment done by the lady Len Hua in MIT in 2002. She brought down the speed of light to 17 meters per second. And in 2007, Matthew Sellers and his collaborators in Australian National University stopped light in a material called metamaterial. This is Len Hua's experiment. She had a supercooled rubidium vapor, and then she sent light through that, and light slowed down like this. Okay? Light actually stops here. The light comes here and it stops in this rubidium vapor. And here is a sodium doped silicate crystal in which Matthew Sellers send light from right into this, and these are switching beams. Now, if you send the switching beam along with that, it is open. And if you cut off one of the beams, then light stops there. Light doesn't come out. So you can have a light switch. You can stop light using such nonlinear technology. Okay? And in 2009, we find that Charles Cowo and Willard Boyle and George Smith get Nobel Prize for discovering the eye of the world. This is now the eye of the world. We find the camera chips, CCD camera chips in all CCTV television cameras, and they discovered that and they get a Nobel Prize. And to your information, I've been counting Nobel Prize winners in physics and chemistry in the field of lasers, using laser. More than 30 people have got Nobel Prize, both in physics and, for example, Ahmad Zuhail get Nobel Prize in chemistry, but it's using lasers. So more than 30 people have got Nobel Prize in chemistry and physics using laser systems or laser-related Nobels. Nobel Prize winners are more than 60. Now, here is just a very interesting thing. This is a 14 nanometer gold sphere, and this is a dye sphere 44 nanometer. And then you illuminate it, and the surface plasmon in the gold sphere giving out light, and using this multiple reflection, the whispering gallery mode, it becomes a laser. That's a spacer, surface plasmon laser. So it gives you output both ends. So a plasmon laser can be a miniature nano plasmon laser can be built this way. So that's where I would like to stop my lecture. You may have a lot of questions. If I know the answer, I can tell you. I don't think that I don't think that I have bored you much. These are all part. When history is something which is defined by the perception of the historian. In my perception, this is what I see as the history of light. If somebody tells you history of light, it may be different. So I don't claim any uniqueness, but these, according to me, were the important landmarks in the history of light. So I think I have not bored you much, talked about the 1.5 minutes. Thank you very much. And thank you once again.